Okay, let's try out another example here. We've got some cars um, doing a little crazy race where they've got some serious banking angles. And really, if you're going fast enough, right, you could keep from falling over if you had the right physics conditions, right? So this banking angle is actually keeping them from sliding off the road. You can go a lot faster around these corners because now your normal force is pushing you inward on the curve, right? It's helping you, in addition to giving you some friction force, it's actually in the direction inward on the circle. And the more you increase that theta, the more the greater your component into the middle of the circle becomes, right? And so if you think about it, if this was completely 90 degrees, all of your normal force would be inward, which would be pretty wild. And it would be relative to your acceleration, right? Your normal acceleration would determine how big that needs to be. So um, we're wanting to say we don't need friction at all. How much do we need to bank that angle in order to not slide if there's absolutely no friction? Which can be kind of nice to design around, right? Then you don't have to depend on the road's conditions. If it's wet, it's icy, right? We're saying there is no friction. How banked should we make that angle so that no one's possibly sliding? Okay, so we're going to assume the cars have negligible size, so their dimensions don't matter. They have a mass m. Just everyone has the same mass. And you might be thinking, well, wouldn't it change for the car size, right? The little cars, do they need more or less banking angle? And we'll see by the time we do the sum of the forces equals mass times acceleration, it'll actually not matter what the mass is. We can just use it for all masses, which again is nice because we don't want our road to be determined, it's safe for this size car, but not that size of the car. We can do everybody's mass will work on it, right? And the radius rho. So we're gonna do this one with general variables rather than numbers and a speed v. So if we wanted to do that, let's draw up our free body diagrams. So as this banking angle changes, and I'm going to try and draw some here. As that banking angle changes, right? This would be our plane, and it could be at this angle there. That's our theta. But our normal also changed that same amount from, being straight up and down to now some amount out. And oh, I gotta erase it first. There we go. So as we change that banking angle, our normal force is moving out at that same angle. And really, it's just going to be the normal force and the weight going straight down. That weight's not going to change its angle, right? And so that's it for our forces because we're ignoring friction. We don't want to have to depend on friction at all. We're going to make it all accounted for with the fact that a portion of our normal component is pushing us inward. Then our mass times acceleration. Notice that we are looking at this in a different direction. This isn't the T, right? We're looking at the car from the front angle. So really the T would be coming out of the screen towards you, right? That would be the T direction, the direction of the velocity. So perpendicular to that is the normal force going inward, or the normal axis. And then the binormal, which is perpendicular to the N and the T, going straight up, right? So we've aligned that with gravity straight up and down for the B. T is coming out and N is going towards the middle of the circle, as it always does. So here we go with the B and N axes that we've got drawn up. We don't really need the T axis, right? It's not going to influence how much we want to slide. And so we can sum the forces in the N, and we've got the normal component here times the sine of theta would give us the component in the in direction. So there we have it. And then the mass, we're just going to put it as m still, times the acceleration in the in, v squared over rho. So that's pretty nice. Now in the b, this could help us to solve for in c, right? If we sum the forces in the b equal to 0, because there's no acceleration in the b. So we'd have NC cosine theta going in the positive b direction, and we'd have the weight going downward, so negative in the b direction. That's all of our sum of the forces in the b equal to 0 acceleration times the mass. So between those two, we can combine equations and come up with some good relationships, right? So there's the equations we just came up with. We could solve that, say, for theta, right? If we wanted to plug in NC, plug in NC there. So if you said NC, well, depending on which way you did it, they did it by plugging in NC from this one into that one, I believe. So you end up with v squared over gravity times rho, and your sine ends up divided by cosine, so you can simplify that to a tangent theta, and in the end, simplify that, or solve that rather for theta, you end up with the arctangent of v squared over g gravity times rho. So that could be our theta for any mass, right? Mass, what happened to the mass? It canceled, right? It ended up not in any of the equations, and so right, it canceled out of both of those. So we don't need to know the mass in order to solve for a theta. That's okay for all of the cars to not slide if they're going a certain speed around a certain radius. So that could be useful. We could use that for track design or for insane race car track design and come up with banking angle and not need to know what the coefficient of friction is, what the mass of the vehicles is. It would work for all of them.